In our last video, we started looking at protein techniques, including salting out, how we could get proteins to precipitate out of a solution by adding large concentrations of salt. In this video, we get to look at column chromatography, and in particular, we're going to look at three types. We are going to look at gel filtration, affinity, and ion exchange chromatography. And essentially, we are going to look at how the chemical and physical properties of these various proteins affect how they move through a column. And we're going to exploit those differences between the proteins to be able to separate them. So let's start with the basics of column chromatography. All right, we're going to talk about the stationary phase versus the mobile phase. So stationary phase is depicted here in this whole area that's kind of light blue. That part is packed into this column and stays there. All right, but it's porous. Things can move through it, and hence we get the mobile phase right here that's going to start up at the top, and we're going to pour that through here. And we have our sample. Our sample is either already dissolved in the mobile phase, sitting on top, and the mobile phase will pick it up and carry it through. And so now this stuff's going to move through here and come out the bottom of our column. But as it does so, some proteins will move faster than others, hence the separation. So if we take a look here, here was our column at the left, and then we start pouring the mobile phase through there. And it picks up that sample we had here. So this sample had a mix of some of these green proteins. They really aren't green, but the ones represented by green, blue, and red that we're going to see over here. And what we see is that in this particular case, the ones we have shown in red tend to move through faster for whatever reason. We're going to look at those reasons. But right now, just in general, they're moving through faster. So if we collect successive samples, the first one might have no protein, right? That was this part. And then everything's still running through. The next one has no protein, but oh, hey, look, that next one has whichever ones are symbolized by red. Then there's that one. Oh, that next one has the blue protein. And so now we have separated these, right? We've got these things coming out, and now they're in different samples, so we can further study them. Okay, I said we were going to look at three types. The first one we're going to look at is size exclusion or gel filtration chromatography. These are going to separate by size. For our stationary phase, we're going to use these beads of cross-linked polymer material. So you've got all these little beads, and they have all this polymer that's cross-linked. And the important piece of that is that when you look at this, there's all these little openings. And depending how much cross-linkage there is, you might have big openings or you might have only little openings. And we're going to pour our solution, the mobile phase, through there with our sample. So if you look right here, our sample has some smaller pink, let's blow that up a little bit, smaller ones shown in pink and some bigger proteins shown in green. And if you look at this picture, it's interesting because people often think, well, clearly the small ones would move faster, but you've got to remember all of these little openings. It turns out those small ones, right, can kind of move into those beads. They can move into these openings and get caught up for a little bit. They'll eventually come out. But the big ones are excluded from those openings. So they take essentially a straighter path down. They might go just kind of almost straight down, whereas those pink ones, maybe they're up in that bead. Oh, now they're in that bead. Oh, now they're in that bead. And it takes much longer for them to move through. Okay, so if we were to look at this, what we would see would be that those big ones will come out first, And then if we keep flowing liquid through here, eventually those small ones will make their way all the way down. You can see that here. We've got the amount of the mobile phase we've put through. We've got protein concentration, and we can see that, wow, it took some amount, some volume to get out those bigger molecules, but it took even more to get to the point where the smaller molecules. I could have put time on the x-axis if I had wanted to. Okay, we would have gotten the same thing. All right, so size exclusion chromatography. There is one. Affinity chromatography. So this is a great process if you have some protein that very specifically binds to some ligand. Okay, so if you know, so we are showing here this substance S shown right here. It's these little yellow, look like Pac-Man, right? Um, and they specifically bind to a protein. So if you look at the protein sample we're putting through, we've shown it with three different shapes, right? Little triangles, little rectangles, little ovals. Well, those triangles bind right here to this substance. Now we have taken this substance and we have attached it to our stationary phase. Whatever we have for our stationary phase here, those yellow pieces, okay, are not moving. They are staying there. And as this moves through it, those ones that fit, that bind to it, will stop and get stuck, whereas the other ones will move on through and move out. Then eventually, what we'd like, right? Hey, well, we want to be able to get these out. We wanted to isolate these. So what we can do is we can pour through a bunch of that same thing it binds to in a mobile phase, something dissolved, so those can flow through. They're not tied on there. They grab those proteins, carry them down here, and then we'd have to release them at some point. So that's affinity chromatography. It can, if you've got the right pieces, right, it can very quickly give you a very high purification. All right, and then ion exchange chromatography. So now our stationary phase, that's shown with kind of these big ovals here, or not ovals, these big circles. Our stationary phase has a net charge. It could be negative, it could be positive. In this case, we've shown it negative. And if we have a protein of interest that we want to get kind of caught up in this column, we want to isolate it, then we're going to pick a pH where we know that protein would carry a charge that's opposite to the resin. So in this case, since we have a negative resin, we're going to pick a pH that will give our protein of interest a net positive charge. So if you remember, when we looked at amino acids, we talked about how we could calculate their charge based on pH, right? Will they be mostly protonated and maybe have a more positive charge? Are they mostly deprotonated? And it was all based on those pKa values. Well, now we're going to use that, okay? And we're going to say, wow, I want this thing to have a positive charge. Let me pick a pH where that's true. Over on the right, we've shown two proteins, one as a net positive charge. It's going to be attracted and get caught up, and one with a net neutral charge that's going to move on through. A net negative charge would also move on through. Okay, and then if we want to eventually elute this, get this to come out, we can use that salting out idea. We can essentially overpower this by just putting in a ton of salt, and the salt will displace those proteins and they will come out. All right, so we're showing that here. We put in lots and lots and lots of salts, and they essentially grab up all those attractive spots on those negative ions, and the protein comes out. All right, last thing, high pressure liquid chromatography. So we can use all of these columns, the resolving power of any of these columns is very much based on the size of the various beads. So if you have very fine beads that allow more interactions, then we're going to have more resolving power. It's going to take longer for everything to go through the various columns. So if we go back up to a column, if we have tons and tons and tons of tiny little beads, we're going to have better separation. But it's also going to take a really, really, really long time. Okay, if actually I'm going to scroll all the way up here. So we can get this separation. This separation would be even better if we had lots and lots and lots of tiny columns, so it would take longer. It'll be worse if we have a lot of big beads that we've put in there. These things might not actually be very separated. So high pressure liquid chromatography kind of takes care of that by using these very, very fine beads, but then it uses a high pressure pump to move the liquid through to speed it up. All right, next up, gel electrophoresis.